So the outline for the talk is I'm going to provide a motivation and an introduction. I explain what Barkhausen noise is and look at the model that we've developed to help explain the behavior of Barkhausen noise under conditions of uniaxial applied stress, as well as strain effect and angular dependence in ferromagnetic materials, which tell us the direction of the magnetic easy axis in these materials. And then I'll summarize what I've presented. So first, the residual stress in steel materials is a critical factor to monitor, for example, in oil and gas pipelines, submarines, and aircraft landing gear. And these are just some examples of some of those applications. But current inspection methods such as neutron and X-ray diffraction can be costly. We can't actually transport a nuclear reactor, provide us with neutrons, and X-ray diffraction is only provides a very thin surface measurement of X-ray and requires surface preparation and takes some time. So the proposal was originally to look at magnetic Barkhausen noise because it was seen that it was sensitive to stress and could identify areas of high tensile residual stress. And in fact, it is used to inspect aircraft landing gear. So the characterization of residual stress, of course, is a key element in identifying susceptibility of materials to stress corrosion cracking, plastic deformation, limited ultimate tensile strength, and fatigue fracture limits. We'd also be interested in inferring other material properties of steel, including hardness, temper embrittlement, core loss in electrical steels, and texture. That's orientation of grains inside of manufactured steel product. So magnetic Barkhausen noise is the term that is given to abrupt changes in domain configuration that occur when a ferromagnetic material is magnetized. And typically we measure surface magnetic Barkhausen noise because that's really the non-destructive way of examining a structure. Some people use encircled Barkhausen noise where the situation allows it. Most of the measurements are done with a U-core dipole electromagnet, and at the center is a pickup coil such as a coil or a Hall probe, and the signal on your right is this hash of stochastic voltage events that arise, and we can do various things to analyze that signal, including integrating it, the voltage squared signal with respect to time, that is, give us an energy signal. Normally an RMS voltage is taken, and of course the square of the RMS voltage would be proportional to the energy signal. And I've also shown there the Barkhausen noise envelope, which some other investigators also use. The phi dt, of course, is the time rate of change of the field. So where does Barkhausen noise appear? Well, it appears in hysteresis curves, or when we examine or see hysteresis in ferromagnetic materials, when we apply a field H and measure the magnetic flux density, if we were to amplify or magnify a small region of that hysteresis curve, we would observe that this hysteresis curve is not a smooth process, but occurs in little jumps. And those little jumps are Barkhausen noise. Well, how does this relate to stress dependence of interest to us? Very early on, observations were made by Buttle et al. That Barkhausen noise changes with applied elastic tensile stress, in this case for the field applied parallel to the stress direction, and is observed to reduce at about 1/3 the rate for the field applied perpendicular to the stress direction. And so this was viewed as being something that could potentially be useful for examining stress in materials. But how can stress and angular dependence of Barkhausen noise response be explained? Well, to do that, we need to look at basic domain configurations. Ferromagnetic materials consist of domains where spin moments are all aligned in the same direction within a domain. But really, we have to consider the entire energy of that system. So there's the exchange energy, that's the spin-spin interaction between the 3D orbital electrons and steel. That's a quantum mechanical effect. The magnetostatic energy, or the demagnetizing fields, this is where the field lines come out of the sample, and that costs energy. The crystallographic anisotropy energy is the energy of the interaction of the spins with the crystal structure, which is via spin-orbit coupling. And so there are preferred directions for the spins to be aligned in the cubic structure of iron. Magnetoelastic energy is the energy that arises due to stress applied to the steel. I'm going to talk about domain walls and explain what they are. They also have an energy element. And of course, if we apply stress, in particular 180-degree domain walls, or the spin moments rotate by 180 degrees, are also affected by stress. So the total energy then is the sum of all these terms. So beginning with the exchange energy, we see in this diagram the Bethe-Slater curve, where iron is near the top. So if I actually apply stress to iron and separate the atoms further, as demonstrated here, the A over R, the exchange energy actually will increase, i.e. it'll become more magnetic. The opposite is true for cobalt, which is now over on the other side, and likewise for nickel. To increase the energy, the magnetic energy for nickel, I would have to apply a compressive stress. And in fact, some of the other materials, such as manganese, we can actually make ferromagnetic by applying the stress. So as I mentioned, magnetostatic energy means that the field lines come out of the grains and they go into space, and that costs a lot of energy. So this is the saturated domain, or single crystal, we can call it. That's a saturation magnetization, and the energy cost associated with those field lines is high. If I add a 180-degree domain wall, or separate these two, I actually reduce that energy, and I can continue to reduce that energy by adding more 180-degree domain walls. Of course, there's also energy associated with 180-degree domain walls themselves. This diagram here shows what happens for a 180-degree domain wall. Basically, we start with the first domain on the lower left, and then go up to the upper domain on the right. The 180-degree domain wall is the general rotation of spin moments inside the wall, and for an iron crystal, that is about 300 atoms or 800 angstroms. We can also rotate just by 90 degrees, and that would be about half the extent and half the energy, and would produce a 90-degree domain wall. So now we end up in this figure with a domain configuration for a cubic crystal of iron, with the spin moments aligned along the 1, 0, 0 directions in the cubic crystallographic structure. We're just seeing a two-dimensional projection, but this structure is completely flux closed, so we have no magnetostatic energy associated with it. It's under zero applied field, clearly, and we have both 180-degree domain walls and 90-degree domain walls, where the spin moments are rotating by 90 degrees. So then what is Barkhausen noise, or how does that come about, or what happens when we apply a field? So if we apply a field along a crystallographic 100 direction, what we get is the 180-degree domain wall moving due to the force applied by the field, which basically increases the energy. So there's a dx, the EDX, I should say, and that force causes the domain walls to move, but they don't move very smoothly. In fact, they're often, except for electrical steels, they're going to be on pinning sites, number one, and they're going to hit another pinning site, number two, and it can be explained in terms of a potential energy expression where the domain wall actually jumps from 1 to 2 very rapidly. And that is our Barkhausen event. The net result of that is a magnetic dipole moment that forms, and that, of course, results in magnetization of the material. So we can relate this to our initial magnetization curve if we were to apply a field to a steel material. Down at the bottom, region A, we're in the Rayleigh region, and we have some reversible processes going on, so we can move 180-degree domain walls very easily. I should mention that most of the Barkhausen noise, or the biggest signal, is going to come from the 180-degree domain wall motion, because it results in the largest magnetization change. 90-degree domain walls can also contribute, but they're going to make a smaller contribution. There's the 180-degree domain walls effectively have more energy, and so they're also the first to move. And so as we continue to apply the field, we're going to make the 180-degree domain walls move to position B, and that's going to form a magnetic dipole moment, as shown by the dashed lines. And as we continue to increase the field to C, we're going to complete all the motion of the 180-degree domain walls, and we're going to be left with just 90-degree domains. And those 90-degree domains then are, most of that motion from C to D then is at the knee of the initial magnetization curve. Finally, going from D to E, the field direction is a little bit off of the crystallographic orientation, and then what we have is spin vector rotation, where the magnetic field induces the spin moments finally to rotate in the direction of the applied field. And of course, if we were to return and turn down the field, we would get our hysteresis. So then what is the source of magnetic Barkhausen noise? Well, it's the abrupt motion of domain walls between pinning sites during magnetization, as I explained. We can measure that abrupt motion by picking that signal up through a pickup coil, and according to Faraday's law, B is equal to minus N d phi dt. Now, models incorporating 180-degree domain wall motion have been successful in describing most of magnetic Barkhausen noise behavior by considering the distribution of orientations and field components of domains bounded by 180-degree domain walls, and also the number of 180-degree domain walls. That distribution can be used to describe the angular dependence of magnetic Barkhausen noise and determine the direction of the magnetic easy axis. It's easiest to magnetize a steel sample when in the direction that most of the 180-degree domain walls are aligned. So what is the Barkhausen signal that we measure? Well, basically, when we apply a field, we get a dipole moment, and that dipole moment has two components. A radial component, which is the one that we would pick up with the surface pickup coil, and also a Z, or a component in line with a magnetic dipole that we would get if we were to encircle Barkhausen noise measurements. So how can we explain and apply this to the characterization of steel materials? Well, Bertotti in 1985 proposed that we should consider regions of independent magnetic behavior. We extended that model to say that those regions of relative independent magnetic behavior are actual single grains in typical steels. So in pipeline steels or submarine steel, for example, we have 5 to 20 micron grain size, and we can go up to 100 microns in non-oriented laminate steels, and of course millimeters or a centimeter in grain-oriented steels. We also considered these are volumes of correlated domain behavior. They're characterized initially at zero field by flux closure, and they exhibit the properties of a single iron crystal. Energy is minimized within a magnetic object, and we ask, how can this help us to understand magnetic behavior? So this would be our magnetic object, very similar to the diagram that I presented earlier. I now have dimensions of height A, width B, and thickness T. And can we actually apply an energy calculation to that? We also need to, of course, consider the magnetic object along with a number of other magnetic objects. And again, as I pointed out, it's the majority of crystallographic easy access directions in which the 180-degree domain walls lie that determine the direction of the magnetic easy axis in this steel material. When I apply a field, I end up with a net magnetic moment, and that's actually not necessarily all along the applied field direction. It may be at other angles as well, and we can actually measure these off diagonal components, and that has been done in the literature. So the 180-degree domains along the crystallographic easy axes grow at the expense of the other domains via domain wall motion. So then we ask the question, well, how does stress modify these domain configurations? And for that, we go and actually calculate the total energy of our magnetic object. And we have the magnetoelastic term at the top here. And for that, we consider the volume of the 90-degree domain, the volume of the 180-degree domain, and we can input that into the expression. And here the variable that we're really interested in is n, the number of 180-degree domains, because n is actually going to affect our Barkhausen noise signal. The more 180-degree domain walls we have means the larger, the more Barkhausen noise that we measure. We also have the energy of the 180-degree domain walls under stress, and then we can consider the total energy, an equation at the bottom of the page here that combines all of those terms for our magnetic object. Theta is the angle of the stress with respect to the crystallographic 100 direction. Now, if I consider the difference between two domain configurations where I have n equals 1 or 2 180-degree domain walls and n equals 3 or 4 180-degree domain walls, then I can actually take the difference between n and n plus 1, and I come up with a change in energy between those two domain configurations. And I can say, well, if I let that equal 0, then what I have is the threshold for the addition of a new 180-degree domain wall. And so this is the idea that we would have a magnetic object with two, for example, 180-degree domain walls, and we apply stress and actually introduce a third, or we find that there's a lower energy state for the third one, for n equal 3. We have to realize that when we're doing Barkhausen noise measurements, we're applying a 50 Hertz cyclic field, for example, and that's all continuously rewriting the domain structure underneath, and that's what we're actually measuring. So the lowest energy state then is one where we can increase the number of 180-degree domain walls with applied stress. And what is shown here is a series of curves for different grain sizes going from 5 to 25 microns. And in that calculation, we are adding 180-degree domain walls shown by the points here. Notice that the curve is not linear, but actually tends to saturate or slow down. And that's because it costs energy to add a 180-degree domain wall to the magnetic object or the domain structure. So we can't go on doing that indefinitely. And in fact, we are also limited by the yield strength of the material, which for our case was about 500 megapascal, shown by the sigma y in the lower half of the figure. Notice that for smaller grain sizes, we can add fewer 180-degree domain walls, but for larger grain sizes, we can add more. And those curves are given by the expression up in the upper left hand corner of the figure. So how can we investigate the effects that this might have on Barkhausen noise? And to do that, we consider an experimental setup where we have a uniaxial applied stress, sigma, that is at some orientation with respect to the magnetic easy axis of the material. There's a pickup coil sensor in the center, and we're rotating our U-core magnet so that we apply the magnetic field in different directions. We're considering a mild steel sample. So MBN in a mild steel sample under uniaxial stress. Now the stress in this diagram is being applied perpendicular, vertically, perpendicular to the easy axis of the material, which is in the rolling direction shown as given by the magnetic energy polar plot that we see here. And we're going from 0, 60, 120 to 220 megapascal. And we observe a steady increase in the direction of applied stress. But perpendicular to the applied stress direction, we see a decrease. And at about 60 degrees to the applied stress direction, we in fact don't see any change at all. And that is due to Poisson's ratio. If we consider the strain, remember this beta Slater curve, the strain increases the magnetization of the material. And in the direction of applied uniaxial stress, the strain is going to increase the magnetization properties, also the 180 degree domain wall population, therefore, but perpendicular to that, it will reduce it. And that value comes out to about 0.28 or 0.29 and is in exact agreement with what we expect from Poisson's ratio. So how can we explain this angular dependence in these materials when we apply H in a certain direction with regard to the net magnetic easy axis? It's the projection of the field along the 180 degree domain wall that causes the domain walls to move. And of course, those domains that are most closely aligned will form the largest magnetic moments and therefore the largest Barkhausen signal. That angular dependence can actually be described by the equation at the top. For single easy axis systems, we get a cos squared theta expression for the magnetic Barkhausen noise energy variation with angle, where phi sub e is the direction of the easy axis. Alpha is an angular dependent contribution that should be at the beginning of the expression, and beta is a contribution of the angular independent background. We can also apply that to more complicated domain structures where we might have superimposed textures or easy axes, and in that case we will see higher order interactions. So in this particular example here, we're applying a stress perpendicular again, most to the easy axis direction, just like the one that we saw before. This particular sample was an octagonal sample, so the stress was not purely uniaxial, it was a little bit biaxial, but nonetheless still shows some of the basic properties. We can increase the Barkhausen noise substantially when we apply stress perpendicular to the easy axis. Again, this relates to it costs more energy to add 180 degree domain walls when there are already some there. So in this case, we get the biggest change in Barkhausen noise by applying stress perpendicular to the easy axis. Compare that to applying Barkhausen noise stress, uniaxial stress parallel to the easy axis. And what you see is that the Barkhausen noise does not increase as much at all. We're going here from 6 megapascal to 202 megapascal with only a very small change. In contrast, when I apply compressive stress to this sample, I see a very large reduction. And when we apply stress at 45 degrees to the easy axis, we get something that's going to be in between the two cases. And in fact, if I plot the peak amplitudes as a function of stress for the tensile and compressive stress condition for relative to the easy axis direction, I do in fact see that I can still add more 180-degree domain walls in magnetic objects or grains where there aren't as many, fewer when I'm aligned with applied stress direction, but I get a big effect from compressive stress. And at 45 degrees, we get a nice linear variation, which is just the average of the two. So to summarize our results and observations, the micromagnetic technique, magnetic Barkhausen noise, is being developed for characterization of ferromagnetic steels. And the application of uniaxial tensile stress and compressive stress in some cases was used to investigate changes in the domain structure that in turn modify the magnetic Barkhausen noise signal. So the application of stress tells us how the domain structures change, and the implications of this are that we should be able to characterize the magnetic properties of materials if we can put in more values into, or more information into our model, including grain size, texture, and so forth. We consider a model that considers regions of independent magnetic behavior, magnetic objects associated with single grains in the polycrystalline steel. And a number of these magnetic objects were used to describe observed magnetic anisotropy and changes in magnetic anisotropy with stress. And the observed effects of stress on Barkhausen noise signal are consistent with the removal or addition of 180-degree domain walls within a magnetic object associated with typical grain sizes in steel. These are the references for the presentation, in case you're interested. And this work was supported by the Natural Science and Engineering Research Council of Canada, RMC Academic Research Program, and Defense Research Development.